Hi, Bobcats. I apologize for having to do a recorded session this morning instead of doing our regular live session. My daughter had an orthodontics emergency and the orthodontist was able to get her in this morning, and so unfortunately there was no other time available. So what I'm planning on doing is posting this lecture in lieu of our problem solving session. This will probably be long enough that I'll have to split it into two separate videos on YouTube. So you should be receiving two links. So it's not just this one, there'll be one more that follows up on it. So today we're doing the recorded one instead of the live problem solving session, and I'm having to move my office hours to 2 to 3 p.m. today only. Tuesday, Wednesday, and Thursday, my office hours will be at the normal time. Wednesday, we'll have our normal 8 a.m. problem solving session, and it will focus on exam 2. Thursday, Examity will be open all day for you to take the exam. Remember, with Examity, you need to schedule in advance. So if you have not already scheduled a session, please, please, please go schedule. Exam on Examity will close Friday morning at 8 a.m. So it'll probably be about 6 or 6:30 a.m. It would be the latest time available on Examity to give you enough time to check in and then take the exam. If you sign up with Examity and then something just goes horribly wrong and you're not able to take it, your internet connection dies, there's Canvas crashes, heaven forbid, but that happened before spring break when some of my colleagues were testing. You know, some disaster like that strikes. So you've done your duty, right? You've signed up, you've made the connection, and then something fails. You can do the emergency Zoom session at 8 a.m. on Friday. Okay, so what are we talking about this morning? So this lecture is replacing our Monday morning on March 22nd, 2021 lecture or problem solving session, and the topic is going to be over salts because this is the spring of 2021 and we've missed a bunch of class days due to Snowmageddon. Salts are one of the spots where I am shaving off some of the objectives, so stay tuned so you can see what you are and are not responsible for when it comes to salts. Okay, so our first and only objective here says to calculate the pH of salt solutions. I think probably a better way to phrase this would be something more like classify the pH range of salt solutions. So we're not going to do the actual calculation of coming up with a number for the pH of a salt, except for one kind where you don't have to do any calculation. We just know what it is. For all of the rest, what we're going to do is we're going to say it's acidic or basic or neutral, but if it's neutral, then we know it's 7 without doing any calculation. All right, so what is a salt? One of the ways that salt gets defined is that it's the product other than water in an acid-base neutralization reaction, right? So this chemical reaction that is being outlined here is a neutralization. And if you have an acid reacting with a base, you get a salt, and very often water, but water doesn't have to be a product. In order to get water as a product, you need to have a Arrhenius base, like a hydroxide base. If you have a Lewis base salt, you'll get a salt, but water will not be produced because you don't have the free hydroxide ion that you do in an Arrhenius base. But here is a more useful way to think about salts. A salt is just an ionic compound, right? And an ionic compound is going to have a cation, which is the positive part, and an anion, which is the negative part. And we can think of the cation as coming from the base, and the anion is coming from the acid. So the acid will give or gives us the anion. So as an example, if the acid is hydrochloric acid and the base is sodium hydroxide, the salt we get is NaOH, and then of course we get water. And I'm writing water that funny way, HOH, because that's usually more convenient for balancing these neutralization reactions. If we think of it this way, this neutralization reaction is a simple double displacement reaction. Remember when we write the salt product, in the formula, the cation, the positive one, has to go first, and the anion, or the negative one, goes second. So even though on the left-hand side of the equation, sodium, oh, whoops, boy, that was a bad mistake. It's not sodium hydroxide over here, it's sodium chloride over here. So the anion there is sodium chloride, and that chloride ion goes second, the positive sodium ion goes first. So more or less any ionic compound can be thought of as being a salt if you can imagine an acid that gave the anion and a base that gave the cation, right? So this sodium ends up being the cation, and this chloride ends up being the anion. I want to emphasize that pattern because that's going to be really useful for predicting the pH of the salt if we can reverse engineer it. If we can start with sodium chloride and say, oh yes, sodium, that came from the base, that must be sodium hydroxide, and that's a strong base. Chloride, that must have come from HCl, which is a strong acid. So if we can reverse engineer it like that and then classify the acid and base as strong or weak, then it's real easy to tell what the pH of a salt is. Salts are also strong electrolytes, and I just pulled this image off of the internet, Creative Commons. It is showing an apparatus that's set up to demonstrate a non-electrolyte, a weak electrolyte, and a strong electrolyte experimentally. It all has to do with how much that light bulb lights up. If it's a non-electrolyte, so the light bulb doesn't light up. If it's a weak electrolyte, like a weak acid or a weak base, you get a little bit of current flowing. And if it's a strong electrolyte, you get a lot of current and the light bulb lights up really brightly. But what I really want to focus on is the particle picture. And if you look inside the beaker of a strong electrolyte, what you have is 100% ions. All of those particles dissolved up there in the solvent, most often water, are going to be those particles are fully ionized. So the cations and the anions have separated and they become the charge carriers which complete your electrical circuit. If you have something like a weak electrolyte, which could be a weak acid, if you look at the particle picture here for this weak electrolyte, you have full molecules, which are the two particles stuck together, and then you have a few charged particles, the positive ion that's there in red and the negative ion that's there in black. So you have just a little bit of charge carriers present, so you do complete the electrical circuit, but you don't have a lot of current flowing, so the light bulb doesn't light up very brightly. When we are talking these strong electrolytes with 100% ionization, we are going to use a one-way arrow. That means that what we actually physically have present in the beaker is all broken apart. It's all the product, what we write after the arrow. But when we have a weak electrolyte, we're going to use the equilibrium arrow. And in the case of in the case of weak acids and bases, like 97% will lie on the reactant side and only about 3% will be on the product side or ionized. All right, let's take this one step further. How do we represent a strong or weak electrolyte with an equation? So if we were to have a salt, which is a strong electrolyte, and let's just use the classic example of the salt, which is sodium chloride. When sodium chloride dissolves in water, I'm just going to put water here, we're going to get sodium ions and chloride ions. This is a one-way arrow, so when you peek in that beaker and you look at the particles, it is 100% sodium ions and 100% chloride ions. Now, if we were to have a weak electrolyte, something like, oh, let's keep it simple. Let's do hydrofluoric acid, which is a weak acid. Instead, the way we would write this is HF in equilibrium with H plus F minus. And we'll have about 97% of what's in our beaker being HF molecules and only about 3% being those H plus and F minus ions. So here's the real big difference. It's in how we write the equations. It is the one-way arrow for a strong electrolyte dissolving versus the double arrow for a weak electrolyte dissolving. And what we're trying to represent here with that one-way arrow, what we have in the beaker is 100% of what we're showing as products in our reaction. And when we have the double-headed arrow, it is mostly reactant with just a hint of product.